Hey everyone, you guys have an assessment for orbital motion. We've been talking a lot about gravitational forces and centripetal forces and things that are orbiting other masses. So I wanted to kind of recap some of those so that you can practice your problems and make sure you do well on your assessment. So the first equation there is the force of gravity between any two masses. You take that gravitation constant, multiply by mass 1, by mass 2, and you divide by r squared. R, remember, is the distance from center to center for any two objects. So if we talk about two objects like myself and the Earth, what we'd have to do here is know the mass of yourself and the mass of your planet and how far away you are from center to center. What a lot of people think is, well, I'm on the surface of the Earth, so I have no distance from the Earth. But technically, if you want to measure from the center of you to the center of our planet, you are a distance away. You are a radius of that planet away from its center. Over here, this r value will be the radius of Earth. That's something that will be given to you, or maybe it's something you'll be asked to solve, but it's 6.37 million meters. If I wanted to find the attraction between myself and the Earth, I would have to give you my mass, so 70 kilograms, and the mass of Earth. So the mass of the Earth is 6 times 10 to the 24th kilograms. So putting those masses in, dividing by that distance squared, please don't forget to square it, and multiplying by the gravity constant, remember that's 6.67 times 10 to the minus 11, I can tell you that you'll get an answer around 700 newtons. So that is the gravitational force from the Earth pulling on me. Remember, due to third law, I actually pull the Earth up with the same exact force. So if I want to find my acceleration, well, I already have my force. I'm going to put 700 in here, and if I want to find the acceleration of myself if I trip and fall, I put in my mass, which is 70 kilograms. So dividing those two, you get an acceleration of around 10 meters per second squared for Earth. But if you look down there at that fourth equation, we knew that that was going to be the answer. We're on Earth, so the gravitational field strength is our gravitational acceleration. So what that means is I can take any of these formulas that you have here, and since they're all force except for that last one, I can set them equal to each other and prove things and solve for things that I want to know. Let's set this equation equal to this equation. And what does that tell me? Well, it says that if I want to find some object's acceleration, I can take F equals ma and equal to m times 10 newtons per kilogram. Since I have a mass on both sides, I can knock out the mass and see that the acceleration of our planet is 10 newtons per kilogram or meters per second squared. Let's set the giant gravity equation equal to ma. Well, if that's the case, mass times acceleration will equal g mass 1 mass 2 over r squared. Well, I have one mass on the left and two masses on the right. What you kind of have to define is which mass are you worried about accelerating. If it's mass 1 accelerating, then I really don't care about mass 1. Mass 2 is causing mass 1 to accelerate towards it. If I switch that up and had mass 2 on the left side, then mass 1 is causing mass 2 to accelerate towards it. Which means that if you take away those masses in our equation here, the acceleration that an object will feel is g mass over radius squared. And this is how we know that we can calculate the acceleration due to gravity on our planet. All I have to do is do the gravity constant, the mass of Earth, and the distance we are away from Earth is, remember, Earth's radius. You put those values in and crunch it out, you should get an answer very close to 9.8 or 10 newtons per kilogram. But let's talk about something in orbit. So when we have things in orbit here, remember, objects need to have a tangential velocity away from their mass. Why? Because they definitely feel a force of gravity. One mass pulls on the other mass, and the other mass pulls back. And if I don't have any velocity, what you can see is that, yes, the masses will pull together, and little mass gets eaten by the big mass. So let's reset that and see what happens with this new velocity I gave the mass. Not enough. Not enough to at least orbit. It started to move, but the force of gravity was too strong. Let's go a little bit faster. Still not enough. So if I give the planet a larger velocity here, it will orbit the other mass. So now I have just enough velocity that I'm being pulled in towards that central mass, but I'm not falling in and crashing. I'm going so fast that there is an inward centripetal force now that is caused by gravity, trying to keep me in orbit around my central mass. So what I could do here, because I'm in orbit, is I could say that there's a centripetal force inwards. The centripetal force is caused by gravity. So what that can let me do is make mv squared over r equal g mass 1 mass 2 all over r squared. And like we did before, what this will let me do now is solve for velocities, radiuses, whatever you don't have enough information to solve. Let's say we're trying to find that orbital speed. What particular speed did I have to give that mass so that it didn't fall into the sun? Well, you have mass 1 and mass 2, that's say Earth and the sun. Over here with the centripetal acceleration, this mass is the mass of the thing that is orbiting. So that is actually the Earth. And if this is Earth's mass as well, it's on both sides. And I can eliminate both of those masses. You can see there's actually a radius on both sides that I can get rid of. So that leaves me v squared equals gm over r. So if I solve for velocity, velocity is the square root of gm over r. This is what we call orbital velocity for any mass. That mass that's in that equation is the central mass. Like if we put the sun's mass in, and the distance you were from the sun, I could tell you how fast you have to move so that you orbit the sun but don't fall in. If we want to know that for Earth, put in Earth mass and Earth radius, and you'll get a new orbital velocity to figure out how fast you have to travel around our own planet. And once you have that velocity from the centripetal force equation, you can put that into your velocity equation down here and solve for the time to orbit, or solve for the radius of your orbit. A lot of things are able to be solved once you find that speed. We gave you the answer key for your orbital motion worksheets today in class. Try using these formulas and practicing problems and making sure you get answers that are close so you can do well on your assessment.